All right. Welcome again to the Ignitarium Webinar series. Thanks for taking out time on this wonderful Thursday. I'm Malvika. I'll be your host for this session. As most of you here know, this is a three-part webinar series on audio AI on low-power hardware. The first part of which you'll be taken through today. There are two other parts which we will be launching in the next few weeks. So part 2 will be around noise suppression, and part 3 will be around sound event classification, all in the context of audio AI. So you want to keep your eyes open for the announcement on these as well. Today we will be focusing on voice command recognition on battery-powered devices. To take you through this, we have our expert from the AI team and our speaker for the day, Kevin Paul. He's a senior staff engineer, multimedia and AI group. Kevin has over 14 years of experience in the multimedia domain. He has worked on audio codecs, audio post-processing modules, development of signal processing algorithms for home and automotive industries. He has been a part of developing multimedia frameworks like GStreamer, Android Nuclear, and Media Foundation. An AI and ML enthusiast with a keen focus on audio, he has led engineering teams to solve complex problems in the areas of noise suppression, voice activity detection, voice command engine, and signal classification problems for the past several years. You can get a glimpse of the work by his team on our audio AI page, the web page, the link to which we are going to share now and at the end of the session. Also watch out for an interesting demo during the session and also some interactive polls. In fact, one should be coming up on your screens right now. Balaji, can I request you to bring up the poll, please? Meanwhile, I will just go through a few of the guidelines for today. Please stay on mute at all times. The video turn off at all times. The webinar will be followed by Q&A. If you have a question, please type it in the chat window at any time during the session. Kevin and his team members will address them at the end of the webinar. Okay. So we're all set. Over to Kevin.
Thanks, Malavika. Good morning and good evening to all. This is Kevin Paul from Ignitarium, and I'm here to talk about the exciting field of audio and the impact of deep learning in building more robust solutions. To start off, let's look at a taxonomy of interest in the domain of applied audio engineering, by which I am referring to the different types of audio and deployment platforms. The types of audio are speech, noise which includes both stationary and non-stationary, music, and sound events. And by sound events, I mean the sound created by different animate and inanimate sources like cough, gunshot, tire screeches, glass break, etc. Among this, as Malavika mentioned, we are going to focus on speech, noise, and sound event in our three-part webinar series. And deployment platforms are the different hardware form factors that is used to process or render audio. Broadly, we have PC server cloud as one class of platform, and other prominent one is edge devices, otherwise known as embedded hardware. Our focus of interest is on edge devices, and based on two factors, it can be classified further. One is whether the device is connected to the internet or if it is offline. The second category is the power source, wall or battery operated. Like our topic for today suggests, we will take a deep dive into audio applications that run on offline battery-operated edge devices, leveraging the best of DSP and AI. Before that, let's look back at DSP and the early use of AI in the field of audio. The use of DSP was aimed at improving the user experience. One of the key use of DSP has been in audio compression and decompression applications, and a whole gamut of pre and post processing functions like gain control, echo and noise cancellation, beamforming, SRC, etc., which are still being implemented using DSP techniques. When the need for applications like speech recognition or sound event classification gained momentum, there were two different approaches to such problems. The first is a signal processing based method, which usually looks for a template in the signal. The event is considered to have occurred if the input closely mimics the template. The second approach uses artificial intelligence as the engine to detect speech or events from audio signals. Classical approach relied on use of machine learning algorithms like hidden Markov model or modified versions of HMM. However, their application and accuracy usually did not inspire confidence with respect to reliability or the effectiveness. And also, the kind of effort and patience required for these kind of solutions was immense, which in turn impacted the turnaround time the market was looking for. What does audio of today and tomorrow look like? As in the case of image and video, deep learning came into the fore for audio only in the past decade or so, actually a little later than vision AI. With the onset of the deep learning era, the accuracy and efficacy of such systems saw considerable improvement just by replacing such classical AI models with artificial neural networks. We observe that there is an increased adoption of ANN-based models. Now we see few applications implemented using the neural networks and being deployed in the field. These audio applications are best implemented using a hybrid approach, a combination of DSP and neural networks. Still, many mainstream audio applications continue to use pure DSP algorithms. To give an example, compression. But there is active research within the AI Open Society in the field of audio compression. And very soon, it is expected that neural networks will play an integral part in all audio applications, helping overcome some of the limitations of DSP algorithm. What are examples of some of these limitations? Let's take the case of offline voice command recognition to understand this. Voice or speech recognition is a very common application, and with the popularity and ubiquity of Alexa, Siri, and Google Assistants, it will soon become a user interface of choice. However, there are cases where privacy or embedded hardware constraints don't allow of a connected voice recognition solution. This is where offline voice recognition come into the picture, where we fixed phrases need to be identified to say. Basically for controlling a washing machine or a coffee vending machine, or probably in a smart office space, etc. In the voice command recognition space, we are seeing customers from the verticals shown here: consumer, enterprise, healthcare, and automotive, with a majority of them in the consumer electronics space. Within this, hearables market is showing high appetite for offline command recognition, and implementing such solution for extremely low cost, ultra low power battery operated devices is quite challenging. In the subsequent slides, we will explore the design consideration and implementation aspects in some detail. The traditional DSP based and the proposed hybrid design has its own pros and cons. If we talk about the DSP based approach, to get the HMM model running, we would need the acoustic model, basically to generate the phonemes, pronunciation dictionary, that too if at all we have multiple language, a dedicated one for each language, and the actual language model trained over a large data. The main advantage of this method is scalability. That is, once a particular language model is trained for a new set of command in same language, additional data acquisition is not required. And after initial development of model, the subsequent ones would be much faster. But I feel there is a long list of disadvantages like inaccuracies due to different accent, dependency on background noise, each language requiring its own dictionary and other modules, increasing the memory as word or language that need to be supported increase. To give an example, a linear increase in step of about 8 KB per word would be required. The proposed hybrid model overcomes all of these limitations that the DSP approach has. But there is a need for data collection when a new set of commands are introduced. But the need for lesser memory footprint and the need for higher accuracies belittle disadvantages and looks to be the way forward for command recognition engines. Customers who wish to deploy voice UI on wall-powered or battery-operated edge devices have to use low-cost hardware. Here in the slide, we have listed two typical configurations of hardware that would fit this case. The basic hardware spec has very low internal SRAM and around 100 MHz processor clock and simple serial wired interfaces, whereas more advanced spec would boast of more SRAM and flash and built-in wireless connectivity on the same chip. The advanced spec allows us to add other audio functionalities like beamforming for multi-microphone cases, etc. Considering these specifications, customers have multiple options starting from MCU with a Cortex M4 all the way to the DSP, FPGA, and custom AI accelerators. Two of key factors governing the selection is cost and power consumption. Depending on the overall system complexity, the power consumption expectations can range from hundreds of millivolts to few tens of millivolts. Presenting Ceptra, Ignitarium's audio AI portfolio, designed for low power devices. Our voice command recognition or VCR software has been designed ground up considering the basic chip specification that you saw in the previous slide. The salient features of our VCR solution is ultra low memory footprint and low MCPS, noise resilience, built-in voice activity detection. Noise resilience is achieved using a unique noise-aware NN model, and the WAD design is using DSP plus a custom neural network instead of the standard RMS energy approach. As I mentioned, the design philosophy is centered around low power. Let's look at the core design principle that would allow implementing the software on the basic chip specification. The architecture of voice command engine can be a CNN based, or it can be a GRU based, or even a combination. And the feature extraction could be MFCC, BFCC, or probably you could train the audio directly, or it can be any spectral features. Trials on various combination of these features and neural network could yield a decent accuracy. But the input data is most important factor which will influence the accuracy of the overall system. The input data to the VCE is dependent on the VAD, or the voice activity detection. The accuracy of the VAD should be at least 98% in any noisy environment to have a good overall system accuracy. The accuracy of the command prediction totally depends on the VAD system giving the full command without any loss of data. To keep the memory and compute tight, our solution uses DSP function for feature extraction, which is implemented for just the required number of spectral features and their derivatives. But the place where maximum optimization is in the implementation of custom NN layers, which we have handcrafted to keep a balance between accuracy and memory usage. We have 8-bit fixed and 32-bit float versions of the model with difference in accuracy of less than, let's say, 1.5% or so. While the core of the solution is the algorithm and neural networks, there are two critical phases that are equally important. One is the front end of the development flow, which is data collection and preparation. And the other is at the end of the pipeline, which is testing and benchmark. Both of these phases can be highly automated. The data preparation phase lends a lot to the improvement of the accuracy. Data collection and preparation is done using our proprietary tool called AudioFarm. The test and benchmarking flow is as shown and is designed for end-to-end testing, starting from input path testing, ground truth validation, pre-processing, and pipeline validation. Model validation all the way for output path testing. The automated test setup has the provision to test both file-based input and direct live voice input. The test can be executed with ease on any hardware once integrated with the wrapper provided as part of the test jig. The Python frontend generates an elaborate test report which gives all necessary performance parameters. The scatter plot shown is a comparison of various networks. Basically, we have accuracy versus the model size. The accuracy result and total model footprint are comparable to the prevalent state-of-the-art models. The implementation is done entirely in C, so there is an ease of portability for our model. As I said, with the ease of portability, we already have a port ready for ARM Cortex, Renesas RX, any RISC-V, and Tensilica DSP. And if at all there is a need for a specific hardware architecture, DSP or AI accelerator would only take a few weeks of effort. Demo kits are available on the hardware board shown above.
Now we'll see Septra in action.
Lights on. Fan on. AC on. TV mute. TV unmute. Fan off. AC off. Lights off.
Hi all, this is Pradeep here, Pradeep Sukumaran from Ignitarium. I hope you can see the screen now. Thanks Kevin for that presentation. Now we can have a Q&A session, so I'll moderate this session. Are you able to see the screen?
No, Pradeep.
Okay.
You need to share the slide. Yeah. It's good now. Yeah.
So if there are any questions, please feel free to type in, or you could ask directly. I'm not sure if unmute is an option right now for the participants. I see a few questions, so I shall start with that.
Hello. Okay. All right. I can wait.
Oh yeah. Okay, Leela. Yeah. Maybe you could go first, Leela, since you.
All right. Like, I mean, it's very high level presentation. I'm a DSP, audio DSP research engineer, so I'm more interested in the technical part of the presentation. So I guess it's a 3-part series, right? So can I expect like more technical details in the upcoming presentations?
Yes. So the way we wanted to do this, Leela, is we wanted to provide an overview and some bit of technical details. Since this is an IP, the more technical details will have to be shared post an NDA. But if there are questions, please feel free to ask. We have the folks here who can answer the questions.
Yeah, I'm more interested in the audio front end part of your technology, like how how you are achieving signal to noise ratio improvement that is required for your ASR to work.
Sure. So if you have any specific questions towards that, we could discuss that, or we could take this offline, depending on the level of details that we would need to share to answer your question. We could do that.
Yeah, sure. Either way is fine for me. Yeah.
Sure. So the subsequent two presentations we do will also be at a similar level of information sharing. Our idea is to present what we've been doing, some results, applications, and look at discussing with potential customers and partners.
Okay. All right. So I mean, you mentioned that.
Yeah, go on, Leela, please.
Sorry, Pradeep. Go ahead.
No, I was saying that there is some information that we have given out in terms of the technical details in the form of an article on our website. So the link that was shared earlier, Nishi, can you share that link again, the Septra page? You could find some bit of information about that, and also there are some articles on our blog. So that could also give you a little more, details.
All right, wonderful. I'll
but again, I think we should take this offline, Leela, where we can give out more details.
Absolutely, Pradeep. Thank you.
Thank you so much. I see a question from Chris Wang. Hi, Chris. You were asking about the languages that are already supported. Yeah, maybe I'll answer that myself. So we currently support, we are been looking at customers in the India, Asia Pacific market, and Japan and US. So English and Japanese language. And since this is a learning-based approach, The language is something that can be supported as long as we have the data set. And like Kevin mentioned earlier, the audio farm tool that we've created is precisely for this requirement, where we would need to collect audio samples from different geographies, demographies, and then use that to train the neural network model. So ideally, all languages can be supported, all types of accents can be supported once we have the required data set. I hope that answers the question, Chris. There's a poll that's probably popped up on your screen now. It would be good if you could take time to answer that. Choose the option. This would help us understand what customers and the market is looking at. This would be interesting information for us. Meanwhile, a question for you, Kevin, that's popped up. Can you hear me, Kevin? Are you there?
Yes, Pradeep.
Yeah. The question is on the DSP part of the software. Maybe this could probably, kind of cater to Leela's question. What are the spectral features that is being used, and how do you choose those?
Okay, yeah. So I'm not going into the specific details. So like everyone, we started off with the favorite spectral coefficient MFCC, did some experiments with it and its derivatives. Then we chose optimally. So we didn't choose, derivatives can keep going on up to 40, however you want, but we chose optimally so that we can restrict it. Then in fact, what we did is we did some research on few extra spectral features that we could add. So it is essentially, it's about a combination of this different spectral coefficient features as well as the spectral features. And one specific part which I could give out is we gave more weightage to the bands where the speech lies in the spectrum. So that I feel gives us much more advantage that way. So that's how we have defined the feature extraction side on the DSP part.
So Kevin, as I understand, then you are essentially like using single microphone, right?
So yeah, current our solution runs on single microphone, but as you know, with our multi-mic and with beamforming and DOA and picture, we could just sort out all this multi-mic options as well. So, yeah.
All right. So the demo that you just showed, was it a real-time demo working with single microphone?
Yes, it is a real-time demo working with a single microphone. Yes.
Oh, wonderful. Okay, good to know that. And then do you also support like multi-microphone topologies?
So currently, we could support, ideally speaking, but we don't have an IP. It's under development for the beamforming, and the DOA IP is still under development. So we don't currently, as of now, we have a multi-mic solution.
All right. So then, speaking about, I'm sorry to the rest of the others if it is going on a too much technical side. So this is just my last question, I would say. So when you say when you are working on a single microphone, then when you are benchmarking with other devices, like an example that you showed is like Google. Google specs, right? How is it compared to Google two mic performance, and then compared to your single mic performances in both stationary and non-stationary noise environments?
Yeah, so see, what we have done is just how the Google speech command to just set up this mention. It's the same procedure what we have done. So they don't have noise to be set at certain SNR, etc. All this criteria has been met when we are doing the benchmarking.
Okay, so you did only Google's FFRS, if I understand very well.
Yeah, so the benchmark is with respect to that, but when we come to the customer front, yes, there have been multiple requests on different kind of noise environments. So I can say that our system support different kind of noises like wind, fan, industrial, etc. And it performs well under these conditions. But I would also say that we had some issues or difficulties where a customer had asked for a kiosk use case in which there were people chatting in the background, or where they
absolutely
where there SNR is really low, let's say less than 10 dB. So in those cases, yes, our accuracies were not that great, but so we are working towards it, and in fact we do have a IGN RNS module, which could be actually added in front of it to reduce suppress noises, and then give it to the command engine. Obviously, we'll need to retrain, and there's an effort there, but we do have a solution to overcome that as well as what we feel.
Okay, good to know that. So when you say IGN, is it like a short form of Ignitarium, or
it's a short form of Ignitarium, and RNS is real-time noise suppression.
All right. Okay, makes sense. Thank you, Kevin.
Yeah, thanks, Leela. And please don't hesitate. You can ask more questions.
Thank you, Pradeep.
Yeah. I see a question now from Georgios. Hi, Georgios. The question is, Kevin, on the quantization methods that we have implemented in this design.
Are we talking about system level quantization or model quantization? So
yeah, I think the question is on the model quantization. Georgios, you can correct me if I'm wrong. Yeah, Kevin. I think you can respond to that for the model quantization.
Model quantization. Okay, probably I cannot give out much of an information there. So that's done by a different set of model optimization team, for which I don't have much of an information. We also did a sort of final model optimization to fit on the hardware, basically on our converting our 32-bit to 16-bit or 8-bit models. So that's the kind of optimization on the DSP side, porting on the hardware that we have done. Model optimization, probably I'll just get back to you with that. I have to ask my teammate to get the exact information on that.
Yeah, that should be fine, Kevin. Thanks. Yeah, there's a question from Atul on how long it would take for a typical porting to a new hardware.
So the typical porting time, I would say it would be really quick, just because of the fact that, like I mentioned in the presentation, our models are completely written in C code. So porting to any embedded devices, it's just a matter of just compiling it and get it up and running. We have done a different porting probably in 2 days and 3 days time. Yeah, so it's as quick as that. To get the stock model with the stock set of words, yeah, it's 2 to 3 days. If at all it's a custom set of commands that you're looking at, it is just the dataset collection and the preparation for it adds time, not the porting and actual optimization and getting on the hardware. That's not going to take much.
Yeah, thanks, Kevin. There is a second question from Chris, which is on asking if on which devices in the market is the solution being integrated in. Maybe I can take that, Kevin. So Chris, the audio IPs that we have developed and voice command recognition is one of them, is actually being evaluated by customers in their labs for different accuracy conditions, environment conditions. And we've also done, we're doing field-based evaluations. The market that we see traction or inquiries is more in the consumer space, home appliances, where you are controlling different devices, and also in the hearables market, the true wireless stereo earbuds, and also smartwatches. So we are in discussions with customers, advanced stages of discussions where field trials are going on, and we've discussed licensing options as well. So hopefully we would see our IP in the product sometime next year.
Yeah, thank you. Yeah, please let me know. Yeah.
Sure, Chris. Yeah. And I see another question from you, Chris. I'll point that to Kevin. The question from Chris is, do we have an AI noise cancellation solution? Is it active or passive?
Oh, okay. So it is not a noise cancelling solution. So it is an active noise cancelling solution. And yeah, we do have that.
So Chris, the details of that would be shared would be a part of the next webinar. We'll announce that soon. And we also have some information already available on our website on the AI-based noise suppression. We call it noise suppression instead of noise cancellation. So there is that information, but yeah, we will have more details coming up in our next webinar.
Yeah, sure. I will try to join. Yeah, but if you have some information you can share in advance, please,
sure.
yeah, kindly share.
Yeah, sure.
Yeah, because yeah, I think yeah, we are finding some active noise cancellation solution. I think which has a strong demand from the market.
Okay. Got it, Chris. We'll do that. We'll have a discussion on that.
Thank you. Yeah.
In fact, we do have a evaluation package that we can provide, whether you can try this out and see if it works in your environment.
Sure. That would be good.
Well, I'm looking for more questions that are popping up. I think there is questions that are coming out on the chat that everyone can see. There's also some direct messages going on. So there is one that I can see, which is, yeah, Kevin, the question is on the number of, typically number of samples that will be required for getting, the accuracies you're talking about for training. What would be a good number of voice samples? Yeah.
So it's a tricky question. So far what we have seen is probably getting 100 unique voice samples gives a good decent accuracy. Like in the case of images where we say use more samples for better, it doesn't always work out for us because we want to restrict the model to fit on the lower resource devices. So instead of having 100 unique samples, if you get 200 unique samples, yes, it is good. But you cannot expect to have a linear increase in terms of accuracy. There might be a small increase. So even you say in the terms of hundreds and 200s, to give you an example, there have been a particular case for one of the Japanese customers where the accuracies were really good, but we just had 30 samples per class. So it is not just about the number of samples, but also how unique the command set is. That also gives a really added advantage for getting the accuracy.
Yeah, thanks, Kevin. While we wait for more questions, we have a few more minutes before the close. I'll just share the results of the poll. So the question that we asked was, what is your top criteria for selection of audio AI software for edge device? We're talking about low power, low cost embedded devices. As expected, it's accuracy that you guys voted for more than power consumption. That's second. Interestingly, unit cost is also an important aspect in terms of the choice of the hardware that goes in, more than the software. Software doesn't play. There's a cost which is the same, mostly the same across different hardware. But we have seen that it's very price sensitive market, the consumer device space. So there is a serious pressure on reducing the unit cost. So that's the kind of challenges that we are trying to solve by keeping the memory low, performance, MCPS or the MCPS requirement to a low number, so that we can go for a hardware which can fit in the other audio or any other algorithms or software. And so there is a unit cost that is also important. But yeah, definitely accuracy is the most important one. Okay, I think we'll give it a minute more for any further questions from the audience. This has been good so far in terms of the participation and the questions. Thanks, Leela, for kicking it off.
Thank you, Pradeep and Kevin. It certainly is very interesting and good to know that what you guys have been doing. I'll follow up, I'll be more on it, and then I'll try to join the next webinar to take the discussion further.
Sure. Yeah. There is a last poll for the day, feedback on this that would help us. Yeah. Thanks so much. for your time today. More information, as I mentioned, is available on our website. Please do reach out to us. We are open for discussions, for evaluations, trying to understand where such IPs can be of use. This is definitely an interesting space, and we will continue to make investments and roadmap plans around audio AI, mostly targeted towards the edge. You can reach us at info@ignitarium.com, or if you happen to know us, any of us directly, please feel free to reach out. Thank you so much all for attending, and hope to see you and more folks join the next